All right, this is the second half of the Monday class on October 26th. So what we're going to learn now that we understand the BOD and what that means and how it works, the application of the BOD is to calculate the BOD concentrations at different points in a stream that receives lots of waste. So here that example is given. As you can see that what we are trying to do here is effect of oxygen demanding waste on a river. You see this is the waste coming in here at these locations. This is the waste locations, and you have this, imagine this is wastewater treatment plants, and that receive all the waste is dumped um, into the river. So that the moment it mixes together, it has lots of BOD, oxygen demand, because of the chemical oxygen consuming chemical. So with time, things the oxygen concentration will deplete. So as the oxygen concentration depletes, it reaches at a point where, as the concentration of oxygen deplete, the amount of BOD consuming chemical or the BOD oxygen consuming chemical also decrease because they are being consumed. That's why oxygen decrease. So this is again the graph of BOD chemicals or the BOD oxygen consuming chemicals. Is the BOD is very high here, and then it decreases as it go forward because they are being consumed. As the BOD decreases, the oxygen concentrations initially decrease a lot, but after a point there are not sufficient BOD. That's why the oxygen concentration will back up again. So as you see, there are different zones. This is a clean zone because this is before the waste, and this is at the very end, farther away from the locations. That's also clean zone. In between, you have different zones. The first one, the most contaminated location, is decomposition zone. The second one, which is called septic zone, where basically your BOD is decreasing, but the DO has not come up yet. So that's why this is called septic zone. Means it doesn't have much fish because they can survive. The oxygen concentration is way lower here. So this is the concentration, the minimum amount of oxygen is in this zone. And then you have recovery zone where the BOD concentration has been depleting. So now your oxygen concentration is coming back up. So that means you will have different kind of fish which can survive at low concentrations. And then the very end, you have again clean zone. So as an engineer, you have to determine how far it is from the waste point. You'll find this septic zone, means the lowest concentration of DO. At the same time, you have to also determine what's the lowest it can get, because that will determine what kind of animals or um, aquatic life will survive in those conditions. So your goal is again to determine the distance until which this the concentration of DOC the concentration of dissolved oxygen will be the least amount. So critical. DC means distance critical, and the concentration at this location for the DO we can call DO criticals. Means that's the lowest amount of DO um, you can uh, expect. So let's solve it. The first thing again, the model wise, you solved this kind of problem before. For instance, you remember you solving a reverse moving this way, and you have a stream coming in, and then you are trying to solve what's the concentrations here. So without any reactions, just the mixing, you can know that no, this is, you can just solve by a mixing model. Same thing coming in, two coming in, and one leaving the system. So that's just mixing model. But what if there is a reaction? So then you know also how to solve it. You remember the for a plug flow reactants, you know that C at a certain distance, Ct is C0 e to the minus Kt. And because the distance here, time is a factor of distance travel, so you can convert that to C0 e to the minus K, and T is basically distance over velocity. So the velocity is the velocity of water here. So this is the reason you can use this concept to solve this one before. Now the difference is here the K is um, the rate at which the BOD is being consumed, or the DO is being dissolved oxygen is being used up. But at the same time, one thing we don't discuss yet is the amount of dissolved oxygen dissolved back inside the water because of aerations. So let's see that one. All right. So now if you see, this is the way to solve it. So Kd is the rate at which dissolved oxygen decreases. But there is another term because it's exposed to atmosphere. Atmospheric oxygen is continuously injecting or dissolving inside it. So that is, you can write K aerations. The aerations means oxygen is mixing with water and dissolving in water. So that's what it does. It increases the DO concentrations. So this is decreased DO concentration. That's one rate. So there are two different rates here. So you have to add both rate in this particular equation and solve it. So let's do that one. The first thing again, there are two rate constant, deoxygenations, the rate at which things are being consumed. Which is already we discussed. So that's KD. And basically, this one T or BOD concentration is initially BOD concentration to the power minus KT. So this is this one before. So that means rate of deoxygenations is, you can write the same thing, d uh, d dlt. Let's going to write that more clearly. So you know that dlt by dt is kd lt. This one and the same time you also know that this is the this DLT, the amount of BOD in consumed is inversely proportional to the amount of dissolved oxygen. Um, is a how much oxygenations, how the rate at which the oxygen is being consumed. The um, consumed. So that's why you could write that the rate of deoxygenations is basically the positive sign. So this equal to Kd, Lt, and Lt is this term. Okay. All right. So that's the one we already know this one. And let's see what happens at the mixing point. At the mixing point means here your things are coming here, which is the river water, and the river water has a BODLR, and that's where you have another water coming in. So that one has a BODZL west, and then you say what is the concentration here. What's the value here? So we call L0 because that's the initial BOD concentration after mixing. So again, because it's steady state, you can say that you can write this one, Q in, C in is Q out, C out. So if you see all Q in is a 2 Q in. So if you see this is control volume, one Q is river waters, QR, and LR, plus another is waste coming in. So that's QW, LW. Should be equal to the Q out. Q out here is a two flow mix, so they are mixed together into because water is conservative, so that's why incompressible fluid. So you can add those up. So the flow rate, so 2 pi mix into another flow rate, and C out is here L0. Now if you solve this one L0, that's how we get this term. So what does that mean is this is the BOD concentrations at that spot before even BOD start consuming because of bacteria. Um, So that's why this is the very first initial concentrations of BOD at that mixing point. But now that a reactor, the batch reactor or plug flow reactor is moving at the speed of u, that's the velocity at which water moves. So that's u is basically the flow rate divided by area. That's the one over area here, bed area. So now you have to solve for this one. How the L0 changes with time. How that L become LT after a distance. Then you can calculate what's that concentration is at different distance. So first, let's before we solve for this one, let's have an example where we just mix without even having to consider what's the concentration at far away from downstream. So the example 6, a wastewater treatment plant serving a city of 200,000 discharges 1.1 meter cube per second of treated effluents having an ultimate BOD of 50 milligram per liter into a stream that has a flow rate of 8.7 meter cube per second and a BOD of its own of 6 milligram per liter. So it's saying that you have a river is flowing at a speed of the river velocity Q river is 8.7 meter cube per second, and then your waste is coming in here, wastewater, that's coming in at a flow rate of q, let's say waste is coming 1.1 meter cube per second. And we know that the BOD concentrations, so we can write LW is let's see what's that amount, 50 milligram per liter. And we also know that the BOD concentrations in the river water is L river is 6 milligram per liter. And then the K value, the KR, deoxygenation rate, KD is 0.2 per day, which is first order reactions. Assume complete and instantaneous mixing. Estimate the ultimate BOD of the river just downstream from the outfall. That means I'm asking what is this concentration L0 is, initial concentration at that mixing point. Again, um, we know the value is basically plugging the mass balance here. We don't have to derive it again because now it's all application. You are allowed to just put the final formula. So basically everything coming in QW, LW plus QR, LR, that's all mixing coming in divided by the flow rate that's leaving the system. So QW plus QR. So again, QW is West is a 1.1. I'm not writing unit just to save time because they are both similar units. So it's going to cancel out. The unit will be just LR unit or milligram per liter. So 1.1 times 50 milligram per liter plus then this is a QR is 8.7 times 6 divided by 8.7 plus 1.1, and this whole term will be in milligram per liter because if you put the unit it all cancel out, the flow rate cancel out from top and bottom. So this value would be whatever the number it is, milligram per liter. The next question is the stream has a constant cross section, so that it flows at a fixed speed of 0.3 meter per second. So that velocity is given 0.3 meter per second. Estimate the BOD remaining in the stream at a distance of 30,000 meter downstream. So what you are saying is asking at a distance of 30 kilometers or 3,000 meters from these locations. So now think of what happens. The BOD is inside the mixing point, the certain amount initially that you calculated. And now it is moving at a speed of 0.3 meter per second. So by the time it reaches that 30,000 meter, the amount of BOD will be consumed, some of them. So how do you know? Well, you know that BOD consumed at a certain rate. So that means you know that LT is basically initial amount time e to the minus KT. The T is the time. So here you don't given a time, but it's given a distance. But you can calculate because you know the velocity, you can calculate how long it will take for that water to reach there. So basically, if you know the velocity, you know the distance, 30,000 meter, you can calculate the time it takes to reach that 30,000 meters, so which is basically d over velocity. So 30,000 meter divided by 0.3 meter per second. So that number would be, let's say, um, 10 to the power 1, 2, 3, 4, 5 second. Okay, and you can calculate in terms of day because your time here is the in days. So that will be 5 second, and you know that one day is 24 hours times 61 1 hour 60 minutes and 1 minute is 60 seconds. So if you do this one, this is second would be one day, you get a number in day. Okay, so that's your time. So now you are calculating what's the concentration on BOD. So you know the L0, you know the K, which is a given 0.2. So L0, put this value here. So minus 2, 0.2 per day. That's the KD. And time is given here. Then you can calculate the BOD concentrations. All right, so you know now how to solve the questions if it is given BOD concentration downstream and upstream as well as the waste, you'll be able to calculate. But that answer is actually not, that's true for the BOD, but it doesn't say anything about oxygen. Oxygen concentration depleted because of BOD being consumed, but at the same time, oxygen is also being reaerated or redissolved because of atmospheric pressure. Because atmosphere has oxygen, it continuously have its ability to dissolve inside in a water which doesn't have enough oxygen. So that's why you have to account for that one, aeration rate. Aeration rate means the rate at which oxygen is being aerated or mixed inside the water. So that K rate, so basically the oxygen dissolve, basically dissolve of oxygen inside the water. So how do you know how much oxygen is being mixed? That depends on the gradients. Gradients means the difference in concentration of oxygen in atmosphere. So this is DO um, atmospheres, and this is DO water. Okay, this is in water. So if you know this difference, if the difference is high, then more and more oxygen will the rate will be much higher. So that's why if you see rate of D variations is basically is a function of Kr variations and the deficit. Deficit means um, the maximum amount of oxygen that can stay in water minus the actual amount, which is the DO here. DO saturation means the thermodynamical maximum because you can't put more water, more oxygen than that in normal conditions. So this is rate at which oxygen is being entered or dissolved into the water. So that Kr again depends on couple of factors. Because atmospheric oxygen concentration is constant, so it doesn't really depends on oxygen concentrations, but it does depends on the velocity. The reason is if the water moves faster, then it will more likely to be mixed because of frictions. It you can see that bubbles. Now that's why the Kr increases if velocity increases. So here the velocity is written as u. This is velocity, stream velocity. But at the same time, Kr also increases if the height decreases. Height means this one. This is height. The reason is if you are deeper water, oxygen is not actually going to dissolve into deeper water. It's the exchange with atmosphere. So if it's shallow one, there will be more exchange in that depth. If you go deeper and deeper, there will be less likely oxygen can diffuse into that deeper layer. So the average stream depth is smaller. That means it will have more likely aeration is higher because of friction and mixing and upwelling and downwelling. Whereas if you deeper, then obviously you can touch that lower surface. The oxygen cannot dissolve or diffuse into that locations faster. So either way, Kr usually is given to you. So that's the table over here. You can use this. Again, I notice this is in 20 degrees Celsius. If you have to convert to other temperatures, you can use that formula before given. So now your goal is to determine the oxygen concentrations. Again, oxygen concentrations is DO2 or DODO is basically aeration rate times the deficit. Deficit again is oxygen saturations minus oxygen actual concentration or the deficit. The reason is the higher the deficit, the more the gradient, the more rate at which oxygen will dissolve. It's the same thing. And think of deficit means the difference in height when it comes to water flow. If, so here the amount of oxygen enter into the stream is the same as the amount of water is falling into a system. That amount of water flow is a function of the difference in height. It's moving from up to down. So that means if your height difference is more, the flow rate of water will go much faster. So that's the exact same rate. Again, there is a positive sign here. The reason is the more the deficit, more oxygen goes. So it both have the same sign. So let's see solve example like this. It says that um, the wastewater in example 6 has a dissolved oxygen concentration. So again, there is a river coming in. There is a wastewater. It says that the oxygen concentration. So you can write that O2 of waste um, or DO waste is 2 milligram per liter, and the flow rate Q of waste is 1.1 meter cube per second. And then you have a river. The river flow rate is 8.7 meter cube per second. And then the river DO, which is we can write DO river, is 8.3 milligram per liter. Temperature 20. Assuming complete and instantaneous mixing, estimate the initial dissolved oxygen deficit of the mixture of wastewater and river water just downstream from the distance point. So we are asked deficit. Deficit again, deficit means the DO saturations, the maximum amount, the thermodynamical limit, minus the actual DO concentration at the mixing point. Okay, DO downstream. So we can write DO downstream, or I can write DO0 like L0. So, well, DO saturation is based on the thermodynamic constant, the solubility Henry constant. Those are constant given. So if you see the tables, what's the dissolved oxygen concentrations in water at 20 degrees Celsius, you'll find that this is 9.1 milligram per liter. That's constant at that temperatures. And this one you have to calculate here. Again, that's the value using mass balance where two stream mixing together. So one coming in, two coming in, and then leaving the system. So I'm asking what is this value is, which is here. So you know this one Q waste, DO waste, Q river, DO river. So basically this is in, two in and one out. So if you use the same concept, this will be QR DO R plus Q waste DO waste divided by QR plus QW. Okay, so that will be 9.1 milligram per liter minus, You just plug all the value. KR, which is river, is 8.3 times DO, I'm sorry, this is 8.7 flow rate. So that's 8.7 times 8.3 milligram per liter plus waste is 1.1 meter cube per second times 2 milligram per liter divided by 8.7 plus 1.1. The reason I didn't use this unit because its flow rate cancel out on both top and bottom. The remaining is milligram per liter. So you just plug the value, you should get that answer. Again, this is just a simple mass balance. You just apply the concept. Now the last one. The last one concept is the concentrations of so we are calculating that particular locations. So again, let's solve this one. We apply. So let's see the mass balance. So first of all, this is a if there was no reoxygenations, that this is more like behave like a batch, like um, a PFR, a plug flow reactor. And for plug flow reactor, that CT is C0 e to the power minus KT, K reactions. If you have just one reaction that consume the oxygens, but here you have actually two reactions. They are actually working oppositely. Means they are in one reaction where it's BOD reactions that consume oxygen. You have reactions that supplying oxygen. So you have to account for both factors. So that's why the deficit, if you write the equation of deficit rate of increase in deficit is so think of this way, there are two factors. Number one, what increase the deficit? That aeration will decrease deficit because aeration is basically adding more oxygen in the system that will decrease the deficit. So that's why you have a second term, KR. Um, that's a negative term because deficit decreases with increase in aerations and deficit. But at the same time, here, that the deficit also increases if you have more BOD. So that will be KD times LT. Okay, that's the BOD concentrations. So what I'm saying here is that if you are looking for the deficit in oxygen, it depends on in one rate where the deficit increases because of BOD. This is BOD, or it can decrease. The deficit can decrease. That's a negative sign because of aerations. Okay. So if you write this equation, substitute LT equal to L0 minus KDT, you will get this. If you substitute here, you should be able to get this value. Now you can solve it for D. This is again this is a time factor here, but everything else is constant, and this is another variable. So this is like a linear differential equations. If you rearrange, and which has the solution, which is D here. So again, you just have to remember this, or you have to write that on your cheat sheet. What it means that deficit is a function of two terms. One is related to the deficit itself, and the second one be related to BOD. So this term is related to BOD. This term is related to aerations. But as you notice, this has also aeration term. Um, so so now question is, if you know the deficit, your goal is to determine dissolved oxygen. Dissolved oxygen is basically your deficit. If you know what is deficit means DO saturations minus actual DO amount, and this one is basically that DO sat minus DO in that spot, in that time. Okay. So that's a function of time. That's why I wrote T there. So that means you can calculate DO at that locations or the distance. Let me take the time out. That way it doesn't confuse you guys. DO would be So if you rearrange the equation, so DO would be DO sat, which is this is saturations minus the entire term on the right side. So you can use this equation to solve for the DO at any locations, any particular spot. And the time factor here is basically the time it takes for the water to move from one spot to another. So that would be distance divided by velocity. Okay, velocity is so this is distance from the mixing point, and this is velocity. Sometimes people write U. In fact, this is written U. So that distance is distance variable. You can write x by the velocity is, I'm going to write u here because that's written in the next slides. So if you substitute d equal to or t equal to x by u, x is distance from the mixing point, then you can get the value over here. This is basically transforming that equations from time to distance scale. Okay. So all you have to do is just substitute t equal to x by u. Okay, x is distance variable. So now what it does, it allow you to calculate the deficit at different locations. Okay, if you plug the value, you know the x value, everything else is given. This is the BOD, these are the rates, and then this is also given initial deficit. Initial deficit is basically the initial amount. D0 is DO sat minus the initial DO initial at that mixing point. So let me write 0. So dissolve oxygen. So everything else is given. These are all given to you. You know how to calculate this value before in the example. This is already thermodynamic constant. So all the terms are given. All you have to do is find the x value and you will be able to calculate the deficit. So now, as I said, one of the things that you normally do is try to find out how far it is from that mixing point. You'll have the critical point, means you have the minimum amount of DO. And for that, you know that this is based on the at that spot the change in DO. If you look at that particular, this is the point of inflation, means that's where the derivative of this equation or this expression is 0. So that means if you write d by dt or dd by dx, here d by dx, if you are writing as a x unit, it should be 0. So then, so that's the inflection point, the derivative of that derivative at the location is 0. Then you will solve this. So if you take the derivative, you take the derivative of this entire right hand side and put it value here. Then you solve it for when t equal to tc. Then you can solve this one. Okay. So that value would be this. So if you know TC, you also know XC. XC is basically velocity, but distance by time is velocity. So this will be time would be, velocity is XC by T. See, there is no critical velocity. So that's why XC is velocity times or U times TC. Then you can calculate this distance. So again, for your equation, all you have to do is write those on your cheat sheet and able to solve this one for deficit as well as critical points. So this is just to show that, initially the deoxygenation rate is very high, the oxygen, because you have so much DOC, and your aeration is, it will start increasing more and more after that critical point because you don't have enough BOD to actually consume it. So that's how the sag curve is generated. So let's solve one example because that's the example that you'll get most of the time. Just below the point of where a continuous discharge of pollution mixed with a river, the BOD is, so basically you're saying there is a river and your waste is mixing just at this point. Your BOD, well, that means you can write L0 is 10.9 milligram per liter, and DO 0 or initial that spot is 7.6 milligram per liter. So here the 0 means that distance equal to 0, that mixing point. Okay. The river wet mixture has a temperature of 20 degrees Celsius. So temperature is 20 degrees. That's just so that you know what's the rate R. Deoxygenation rate. KD is 0.2 per day. And your aeration rate, average flow, the aeration rate is given somewhere. Well, it's not given. So that's fine. Then it's given average speed is the velocity here is 0.3 meter per second. And average depth is so that height that's like the height over here is 3 meters. So you asked to calculate, find the time and distance downstream at which the oxygen deficit is at the maximum. So again, oxygen deficit maximum is that's a curve. Okay, so that's the locations. This distance TC or distance critical. So that's the amount. That's the one we asked, which basically these equations. Okay. So, but again, you know that these equations, you can plug the value over here, get the answers because everything else is given. The only thing you don't know is the aeration rate, re-aeration rate. Well, K air R you don't have it, but you can calculate that because that depends on velocity and height. So if you see this value, what is that equations here? Aerations is this 3.9 um, 3.9 you have divided by let's see 3.9 you have what's that term you have divided by h times 3 by 2, so 3.9 you have h divided by 3.2, and again this depends on the unit of u and h, and if you remember what's the unit is meter per second and meter, so you can't use any other unit because that's how the constant is factored out. So u equal to, so 3.9 u would be meter per second, 0.3 meter per second time 1 2, that's the right unit. Height is, depth is 3 meters. You should be able to calculate that rate as per 1 hour day. Let's confirm it. So as you see, KR is 1 hour day. Okay. So now that you have known all these value, KR value, so let me just check that answers so that it's easier to write in the next page. So that value should be 0.41. Okay. Now you have to calculate TC. TC, if you see, TC is this value. So I'm going to write that value here. TC is 1 over KR minus KD ln KR by KD 1 minus initial deficit KR minus KD divided by KD L0. Okay. So let's see what is KR. KR we just calculate 0.41 per day. KD, this is given, is 0.2 per day. Ln, again 0.41 per day divided by 0.2. So that's why I don't have to write the unit because it can't cancel out. Minus or 1 minus D0. What is the initial deficit? Initial deficit, if you see, is basically the value at that mixing point. Let's see this river mixing. So this is a continuation problem, example 6 and 7. So that's why where we calculate the value. So that means this is the value, whatever that number is. So that one, I'm just going to write that. Initial deficit was 1.5. Okay. So that's the value 1.5. KR again 0.41 minus 0.2 divided by KD is 0.2 times L0. Again, that L0 value you calculate in the different example over here. This value L0, we calculate that value. That number is actually, let me write it down here just in case you, that should be 10.9 milligram per liter. Okay. So 10.9 milligram per liter. So that if you plug all the value and calculate, it should be 2.067 days. Okay. So just to confirm now, you got to have the same unit as L0. This is milligram per liter, this is milligram per liter. So cancel out. This is also similar units. Okay, so this entire term here is unitless. So this one over day, so that's why it become 2.67 days. So now this is the TC, but I ask you to calculate the distance. XC is basically velocity time TC, and which is 0.3 meter per second times 2.67 days. Well, you can multiply unless you convert days to 1 day to a second. So 1 day is 24 hours. And 1 hour 60 minutes and 1 minute 60 seconds. Then it should be, you should get the answer in meter. It should be around 69,000 meter, which is 69.3 kilometers. So that's the value for these answers. And last, find the minimum value of DEO at that critical point. So that at that point, the DEO, the deficit is this. It's given because you know the time. You should be able to calculate this value. So if you plug that value, maximum deficit is let's see, is here. So I'm just going to write the equation here so that you know. KD L0 KR minus KD. Let me see what's that term. E to the power minus KDT KRT plus D0 e to the power minus KRT. So again, D0 is given. So D0 is 1.5 milligram per liter. This is given. That's 10.9 milligram per liter. Everything else is given because at that point t equal to, so this t value is TC, that's 2.67 days, 2.67 days. And KR, you know, KD value, you know. So if you substitute all that value, you should be able to get that. So it's 3.1 milligram per liter. So that's the amount, the deficit. Deficit again, DO saturations. minus the actual amount of DO there. Okay. So you know the DO saturations at that temperature is 9.1. So that will be 9.1 milligram per liter minus DO. So that means if you can calculate DO is 9.1 minus 3.1, so it will be 6 milligram per liter. Okay, again, these are not very difficult questions because once you know what those different terms are, you should be able to calculate anything. So let's solve another example. A uniform natural stream of 2.92 meter deep. So again, this value is h. Flows with an average velocity of 0.4 meter per second, that's u. The stream contains oxygen demanding substance which decay and utilize oxygen according to first order kinetics. Just below the outfall from a waste well, the ultimate BOD, which is basically L0, that's the mixing point. So that one is L0. And the DO is 4.1 milligram per liter. So that's the initial amount of DO. So that's, you can write initial DO 0, which is, let me write the solution. So that's initial DO is 4.1. So that means initial deficit D0 is the DO saturations minus DO at that spot. Okay. And the temperature is 25 degrees Celsius. Temperature is 25 degrees Celsius. And the saturation DO at that time is 8 point, or that temperature is 8.38 milligram per liter. So that means you can calculate this one. 8.38 milligram minus the 4.1. So the deficit would be 4.28 milligram per liter. Initial deficit. KD is 0. This is 0.31 per day. Okay, aerations or reaerations, right? K is 0.76 per day. Both determined at 25 degrees Celsius. Determine critical DO and critical distance, and the DO at 60 kilometers from downstream. Okay. All right. So critical DO or critical distance. That's critical distance is, if you want to calculate critical distance, first you have to calculate critical time. If you know critical time, you should be able to calculate critical distance, which is velocity time. So what I'm going to write is xc is critical times velocity. Okay, and velocity here is given from places. Let's see where is the velocity. 0.4. So this is 0.4 meter per second times this TC has to be in second for you to calculate that. So let's write the value here. So that TC is this term 1 minus KR KD then I'm just going to write it here, ln KR by KT 1 minus D0 KR minus KD KD L0. Okay. So this value you'll get in terms of what the unit will be, whatever the unit of this. So you know that that unit of KD is 1/days, and this is second, so you have to multiply. So this time will be in days. So that means you have to multiply. 1 day would be 24 hours, 1 hour 60 minutes 60 seconds for you to calculate in terms of meter. And again, KR is given 0.76. This is 0.76. This is 0.31. These are kr given. Do is d0. Initial is, this is, we just calculate 4.28 milligram per liter. These are all given. L0 is given here, 25 milligram per liter. Then everything else is given, so you should be able to calculate that value. So if you know the critical distance, you can calculate critical DO. So that's basically, the DO value. What's the equation for DO? Is this. So you put the value DO equal to DO saturations minus entire term. Everything else is given, and the time would be what you just calculate, T equal to TC. Okay. So I'm just going to write that here. Entire term. So for me to is, let me see if I can find that in the. Okay, so let me write the formula. KD L0 KR minus KD, so minus KD, and here time critical TC, because that's the location you are calculating the DO at that critical locations. So minus KRT plus D0. Okay. Again, DO saturations is given, which is 8.38. This is 8.38. You know all these terms. L0 is given, D0 is given, D0 you calculated, that's 4.28. This one is 25 milligram per liter. These are given. KD is 0.31 per day. This is 0.776 per day. And TC you calculated before. So this is calculated in previous step. That means you should be able to calculate that value DO, that critical point. Okay, DO at that critical points. The last question is DO at 16 kilometer downstream. So you don't know what's the whether it's a critical or not, but it's given the distance. So I ask you what is the DO at distance equal to 16 kilometers. That means I ask DO x equal to 16,000 meter. Again, same thing, DO shot. You basically have to write this value, KD L0 KR minus KD. The only difference here is that the time term is basically your distance. You write the time equal to, time is distance by velocity. Okay, so this will be distance is d by, or I'm going to write x, so that's easier for you to remember, x by u minus either minus kr x by u plus t0. Okay, then x by u. Again, x is given here, 16,000 meter. Velocity is given 0.4 meter per second. But one thing you have to change, this is in day, 1 over day. So that means this term, you have to change one term, this one in terms of velocity in 0.4 meter per second, you have to change to meter per day. So let's write velocity. So velocity is 0.4 meter per second. You have to change to meter per day. So let's see. So this is a um, 1 day is 24 hours, 60 minutes, 60 seconds. Second cancel out. So whatever that number is, that would be in terms of meter per day. And you have to substitute here. Okay. You can't substitute 0.4 meter per second because this term is in, I'm sorry, this term is um, in 1 hour day. So you have to always look for the unit, right units. All right, so that's how you can solve it. Again, as you see, these are equations. These questions are easiest one in the sense that you just have to plug the value. As long as you know, you understand um, the different units and different terms. Again, I'm not going to do these examples. This example I have solved already 2 questions, so I think you should be able to solve another 2 questions. Again, everything is given. If you see here, river flow rate, U is given. The speed flow rate is this per second meter cube. So that's the flow rate, that's Q, and the speed is this is U. Wastewater flow, that's basically the amount of waste falling into a river. So that's Q waste is 0.1013 meter cube per second. Again, you have to see this is the flow rate, not distance or velocity. And aeration rate is given, Kr is given, is 2.22 per day, and you know Kd is also given here, 1.8 per day, and if you see assuming that the mixed oxygen deficit is 0, and that so at that point the deficit D0 is 0, and that ultimate BOD at that location above the wastewater outfall from Uruguay is 0. So that means here the L river is 0. There is no BOD, and then that can be discharged if the DO must be kept at 4 milligram per liter at the point 8.05 kilometer downstream. So what you're saying, this is like solving it backward. So it says that arbitrary at a distance of 8.5 kilometers, the value of DO is given already. That's the value is be 4 milligram per liter. So then it says calculate the amount of ultimate BOD that can be discharged. So that means I ask what is the BOD in this wastewater. So what is the BOD of wastewater would be, so that when you mix together and it goes all the way distance, this would be finally would be 4 milligram per liter. So first of all, think of what is that BOD, that equation for DO at that spot would be. So you know DO at 8 point kilometers, 8 point, I'm just going to write DO 8.5 kilometers or 8.05 actually. So I'm just going to correct it. 8.05 kilometers. So that's the value. So that's the x equal to 8.05 kilometers. So that means it will be 8050 meter. That's the x. Okay. So DOx at that spot is 4 milligram per liter. And you know the formula for DO that spot is basically DO sat minus KD L0 KR minus KD KD. This will be x over velocity minus minus KR x over velocity plus D0 fixable velocity. Again, D0 is the initial deficit that's written here. The initial deficit is 0, so this term is 0. Okay, because D0 is 0. So D0 is 0. So that's what is given here. And also it says the initial amount of, let's see, everything else is given. U is given. U value is, let's see, U value is, what's the flow rate? 0.3 meter per second. Again, this has to be written in days because you are using in the formula for KD is a 1 hour day. So that would be 0.3 meter per second times 1 day is 24 hours, 60 minutes, 60 seconds. So that will be, this value would be meter per day. So you know this value. You know this value which is given. KD, KR is given. The only thing that's not given here is, let's see, this value and this value. Okay, so DO shot you can calculate. That's based on Henry constant at 12 degrees Celsius. That value is fixed. So you know that value, you can plug that number based on Henry constant or search it. And L0 value over here that you can calculate. You have example problem before. It's basically one coming in mix, another is mixing. Then what is that value? So L0, you know this one before, LW, QW plus LR, QR divided by LW or QW plus QR. And again, the bar doesn't have any BOD, so this term is 0. So you are just putting this value. And you know the LW, or you are calculating LW. That's what given to you. That's what you are asked to calculate. So if you plug this value, this is a function of LW. QW you know, this value you know. The only thing that's missing is LW. So this is a function of LW. Okay. Function of LW. So that means everything else is given. You just solve for LW. Because this, if you substitute L0 as this unit here, you should be able to solve it. Okay, so I was not intended to solve this one before, but I did it. So again, what I'm going to show here is that you plug the value, everything, and this entire term will be a function of LW. Okay, everything else is given. So now you are solving for LW. Because everything else is given. Okay. Obviously, you are also solving for DO sat, but this is constant at the temperatures. So you have to calculate at 12 degrees Celsius what is the maximum saturation for DO. Okay, the only question I didn't solve is here, midterms. I think if you should be able to solve it.